This is section 2.2, Basic Differentiation Rules and Rates of Change. All right. So let's see where we are here. We are getting to some formulas I think you're going to like. They deal with being able to find the derivative in a much faster way than the definition procedure we went through the other day, where it was the limit as delta x approaches 0 of f of x plus delta x minus f of x all divided by delta x. That gave us the derivative function f prime of x. And we found out that that formula can be used to find the slope of a tangent line to a curve at any point x. So what we're going to do now is start with some basic functions and see if we can find their derivatives and maybe generalize to something as a shortcut, if you will. Okay, so let's talk about the function f of x equals a constant, which you know, of course, is going to be graphed as a horizontal line. So for a lot of these, I'm going to draw pictures and go through the definition, all in an attempt to get you to understand why this derivative rule works the way it does. All right, so for this function, applying the definition, which we hope is the last time we have to do so for any function that is y equals a constant. Now notice that that's a constant, so it doesn't matter what number I put in for x. Whatever I put in, the output is always c. So this will be, when I substitute in x plus delta x into that function, I'll get back c. Minus, when I put x into that function, I'll get back c all over delta x. And of course, that difference is 0. And 0 divided by any non-zero thing is 0. And as delta x approaches 0, that constant, the limit of a constant, is that constant. And I hope that makes sense to you, because no matter what point of tangency we might have, the line tangent to the curve at that point is the line itself. And it has a slope of 0. Horizontal lines have a slope of 0. So the derivative of a constant is 0. All right, so that's our first derivative rule. And when we write derivative rules, we use that one notation I talked about earlier very often. The derivative with respect to x of the function c is 0. And that's a derivative rule which you should commit to memory. Okay, so that's the simplest function to deal with. So if I gave you these examples, y equals 7, what is its derivative? Well, since y is a constant, its derivative is 0. F of x equals 0, the horizontal line, which is the same as the x-axis. What is its derivative? Well, its derivative, since 0 is a constant, its derivative is 0. If s of t is equal to -3, what is its derivative? S prime of t. You notice that I'm trying to use both Leibniz notation, the dy dx, and the prime notation, f prime and s prime so far. Those are pretty standard, at least when I'm doing the problems, how I would label the derivative. Okay, so y equals k pi squared, where k is a constant. What's its derivative? Well, since pi is a constant and k is a constant, the product of k and pi is a constant. And so the derivative of the constant will be 0. Okay. So the next thing I want to talk about is how you raise a binomial to a power, because this will occur in doing any of the limit definitions of the derivative. You'll end up having to do squaring and cubing, etc. this binomial x plus delta x, because that will be substituted in for x, and of course if it's x squared, you'll get that first binomial squared. If it's x cubed, you'll get the second one, and so on. So a review of that is well worth our time. So of course this will multiply out to be x squared plus 2x delta x plus delta x squared. If you've forgotten how to do that, you might write 2 of those and use the FOIL technique for multiplying those. For the cube of that binomial, that answer is going to be x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed. Okay? And then x plus delta x to the fourth is x to the fourth plus 4x cubed delta x plus 6x squared delta x squared plus 4x delta x, have one too many little marks in there. Let me fix that. Yeah, 4x delta x cubed plus delta x to the fourth. Of course, this is one of the last topics, generally speaking, in a pre-calculus course. The binomial theorem is what I'm kind of working on here. There are 2 that I left out, and I'm going to put them back in now. I'll write the original problem over here on the right because I didn't leave myself room. So the one right above, x plus x, delta x squared, would be x plus delta x raised to the first, which of course is x plus delta x. And above that, x plus delta x to the 0. And of course, anything raised to the 0 except for 0 itself will be 1, so there's a 1 up here. Okay, so I want you to look at this set of answers and notice that there's a nice pattern. Whatever this power is that you're raising the binomial to, like the 4, that's the very first power of x. So the first thing in the binomial starts out being raised to the 4th, and then the powers of x from there go down and down and down. So it's cubed, x is squared, x is to the first, and x is to the 0, which is 1. Okay? Then notice that the powers of delta x, the second thing, start out at power 0. So this is delta x to the 0 power, which is 1. Delta x to the first, delta x squared, delta x cubed, delta x to the fourth. And so the powers of the first thing start at n, if we call the power that we're raising this to n. It starts out as the power of n, and that goes down throughout the polynomial answer, and the powers of the second thing start at 0 and go up until the very last power you use of delta x is, again, n. Then one other thing needs to be addressed, the coefficients. I'm going to write in some coefficients that we normally don't need to see, a bunch of 1s. And I want you to think about what pattern is in evidence that would allow you to produce those coefficients reliably. Do you see a pattern? Well, a guy by the name of Pascal did, and he built a triangle like this. Notice the triangular shape of it. And this is called Pascal's Triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. Now, do you see the pattern in how you get that number each time? Well, I'm going to do the next one and see if you figured it out. The next one is 1, 5, 10, 10, 5, and 1. What am I doing to produce that? Well, as it so happens, if you take any two numbers in the triangle that are next to each other, like 4 and 6, and add them together, that sum is between them in the next row down. So look at every single number there. It's the sum of the two numbers above it, except for, of course, the edges of the triangle are 1s. So this continues to be 1, and this continues to be 1, all the way down. So that's one way to explain Pascal's triangle, and how Pascal's triangle allows you to find an expression for x plus delta x to the nth. And if you recall, what you learned, I hope, in pre-calculus is, although that pattern over to the right is nice, if you were raising to the 17th power, you have to build a really big triangle to make that happen. And so we found out that there was actually a shortcut way of writing that. It involved sigma from, r equals 0 to n of n choose r. N choose r is defined to be n factorial over r factorial multiplied by n minus r factorial. And on your calculator, you'll see this as NCR. And that calculation of N choose R, which stands for, the NCR stands for the number of combinations you can produce given N things and choosing R of them at a time. And that's how you get the coefficient. So for example, if I were doing 5 choose 2, I would get 5 factorial over 2 factorial, and 5 minus 2 is 3 factorial and expanding the largest factorial until it matches one of the factorials in the other part of the fraction, and then saying it continues after that. Then the one in the denominator will cancel it, and I'll expand the other factorial, 2 times 1, cancel the 3 factorials, and get 10. And that's this one right here. That's that 10 right there. Anyway, after you do that, you take the first item and raise it to the n minus r, and the second item is raised to the r power. And that summation of all of those terms gives you the expansion of x plus delta x to the nth power. So this is again what we call the binomial theorem. So a little bit of pre-calculus review. I hope you've heard this before. If not, I hope that that was enough of an explanation for you to understand, at least understand enough of it to proceed. So in general, if I wanted to have x plus delta x raised to the nth, this is what it's going to look like. X to the nth plus n x, whoops, forgot to write the n x to the n minus 1 times delta x plus n times n minus 1 over 2 x to the n minus 2 delta x squared, etc. So plus dot 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 means keep going in the same pattern until the very last one is delta x to the nth. Okay, so now what I want to propose next, now that we've reviewed that, is that we find for f of x equals x to the nth, let's find its derivative. The good news is once we found this derivative, like the derivative of a constant is 0, once you know that, you won't have to go through that definition process, because we'll have a shortcut, a rule that establishes how that's to be done. Okay, so f of x plus delta x means that I'm going to put x plus delta x into that function in place of the x, so that'll be n to the nth, minus f of x, which of course is x to the nth, all over delta x. Okay, so now the work we did above allows us to get the numerator all expanded out, at least the first part of it, I mean. So that's going to be from what we have above, x to the nth plus n x to the n minus 1 times delta x plus n times n minus 1 over 2 x to the n minus 2 delta x squared plus dot 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 plus delta x to the nth, and that ends f of x plus delta x. That is, that ends x plus delta x all raised to the nth power minus x to the nth all over delta x. Really long vinculum there. Okay, well, you might notice that in the numerator, there is a little bit of simplification that will happen. This x to the nth minus x to the nth is 0. And so we're left with everything else. And everything else has a delta x as a common factor. So I'm going to factor out a single delta x. So the first thing we'll get is n x to the n minus 1 plus n times n minus 1 over 2 times x to the n minus 2. And I've pulled out a single delta x, so when I had 2, I'm left with one of them, etc. And of course, the delta x powers just keep getting bigger. So every single one of those terms has delta x in it, albeit from a little bit smaller power. In fact, that last power will be n minus 1 because we took one of them away, the one that we factored out. Then, thank goodness, the delta x that was a common factor in the numerator will cancel with the delta x in the denominator, leaving us with nx to the n minus 1 plus n times n minus 1 over 2 x to the n minus 2 and a single delta x. The next one would have delta x squared. The next one after that would have delta x cubed, etc., 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 until we got out to delta x to the n minus 1. So now try substitution. Replace every delta x with 0. The result will be n times x to the n minus 1 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0, because every delta x will turn each term into a 0 until we have the last 0. And so the answer is n times x to the n minus 1. Okay, so what that means is, and by the way, the binomial theorem, n is a positive, well, actually 0 as well, but okay, a non-negative integer is what the binomial theorem uses. So what we've proven so far is that the derivative of any power of x, where that power is a non-negative integer, that's what we've proven so far, that derivative is n times x to the n minus 1. What you may hear me say is take the exponent of x, bring it down in front as a coefficient, and reduce the power on x by 1. That's how I remember this rule. So, what would the derivative of plane x be? Well, that's x to the first, so it would be, I'm not always going to write this, but 1 times x to the 1 minus 1, which is x to the 0, which is 1. So the derivative of x is 1. This one I want to show you graphically because I think it will make sense. Once I've drawn the picture, you'll go, oh yeah, of course. Y equals x. Oh, well, I missed. Yikes. Y equals x. Looks like that. And the slope of the tangent line at any point that I want to pick, like this one right here, the slope of the tangent line will actually be the same as the line itself, because the tangent line to a line is the line itself. And so no matter what this is, wherever this happens to be, the slope of that line, which is the slope of the tangent line as well, is 1. Y equals x has a slope of 1. Y equals mx plus b. M is 1, b is 0. Okay? So that's kind of a good one to know. You might even think of that as a special case because it has an invisible exponent of 1. So you might just want to know, oh yeah, the derivative of x, that's 0. Sorry, is 1. Wow, where did that 0 come from? My apologies. The derivative of x is 1. The derivative of a constant is 0. I think I was looking at one of the examples further on and got my tongue tighter. All right, so if that's the function, according to the derivative rule we just found, which I should probably box that one because that's well worth learning as a derivative rule. And let me write the other one without the extra work. The derivative of plane x we've established is 1. Okay. So using the derivative rule, the one on the left, that will be the old exponent brought down as a coefficient times x to the reduced by 1 power. 3 minus 1 is 2. Doesn't that seem so much faster than the definition using a limit? I do believe so. Now, as it turns out, our proof of that power rule, which is what that's called, the power rule, our proof used the binomial theorem, which only applies to non-negative integers. I almost said positive, but it's non-negative integers. As it turns out, although our proof didn't prove it, you can prove it. We're not going to together in this class, but it can be proven that this power rule works for any value of n whatsoever. It doesn't have to be an integer, doesn't even have to be a positive number. So in part B, where you have a radical expression, one of the things you're going to hear me say quite often is in calculus, we really don't like radicals. So we try to get rid of them as soon as we can. And this is why, because of this rule, you're going to want to rewrite the cube root of x as a power of x. And that's x to the 1/3. So let me over here remind you of some algebraic things that you learned in college algebra. The nth root of x is x to the 1/n. The nth root of x raised to the mth power is x to the m/n. And x to the -1 is 1/x, which means that in a more general sense, x to the -nth is equal to 1/x to the nth. Because remember, in algebra, I hope you heard someone say we really don't like negative exponents, and so we're going to want to rewrite things in a different form. Okay, so if that's what g of x is equal to, what is its derivative? Well, the power rule, as I said, applies to any real number n. So that number, 1/3, will come out in front. Then we'll multiply that by x to the reduced by 1 power. 1/3 minus 1 is -2/3. That's not the simplified answer, but sometimes that will be the preferred answer. So don't think that this is a bad answer. It's just not simplified. So if you're asked to simplify completely, the 3 is in the denominator. And to get rid of that negative on the exponent, I'll take it down to the other part of the fraction, the denominator, and that will let me get rid of the negative on that exponent. Now, although this is true right here, I'm going to accept most of the time for an answer that has a rational exponent like that, like 2/3 over there, that you can use this form of the answer just fine. Okay? I'm really okay with that. But if the problem ends up such that its fractional exponent is 1 over something, I'd really prefer that you go back to the radical. So if it's 1 over 2, it'll be a square root radical. 1 over 3, it will be a cube root radical. Okay, so we're going to leave this answer alone just like that. All right, that's a final answer. That's the simplified answer. But do please keep in mind that that answer, 1/3 x to the negative 2/3, is not bad, and we will use it in that form later. It's just not considered to be simplified. Okay, another thing that we're going to not like is a constant over a power of x. We don't like variables like that in the denominator, so we're going to make it travel to the numerator and be over and under. Well, we'll go ahead and write the 1 this time. And in order to do that, we have to insert a negative. So notice that the exponent takes on the opposite value when you move that power to the other part of the fraction. That's what we did from here to here. To take it to a positive power, we took it from the numerator down into the denominator to get rid of the negative. And here we changed the sign on the power of x to take it from being in the denominator to being in the numerator. So this is x to the negative 2. Now very clearly a power of x. And so its derivative is, according to the power rule, the old power, negative 2, times x to the reduced by 1 power. Be very careful with negatives. You're going to accidentally go the wrong way sometimes unless you're super careful. Negative 2 minus 1 is negative 3, not negative 1. So be very careful about that. Then simplifying this, and again, that answer would be good for some of the things we're going to do, but simplifying this, the power of x can be brought down to the denominator to get rid of that negative sign on the power. And so that would be our final answer. So one of the big things that we're going to be doing quite often is rewriting the problem into another form before we do the derivative rule. And so that's one of the things to look for is, should I rewrite this problem so I can deal with it more easily? And I'm telling you that if it's a radical or a constant over a power of x, like these two B and C problems were, you want to rewrite them as we just did, because that makes it x raised to a power and you can use the power rule. So please take note of that. And then of course we'll want our answers to be in simplified form, which means we never want negative exponents as a final answer. At least that's part of it. Okay, so now the next rule I'm going to offer up without proof. If you have any constant c multiplied by a function, and you're asked to find the derivative of that constant times function of x, it will be simply that constant multiplied by the derivative of the function. So that constant will just come along for the ride, and you'll multiply it by the derivative of the function of x. So let's do some examples. If y equals 5x cubed, its derivative, dy dx, is going to be the constant 5 times the derivative of x cubed. Using the power rule, that's the old power 3 times x to the reduced by 1 power 2. Then simplify and you get 15x squared. Okay, b. Y equals 2 over x. Again, I'm going to rewrite this, and I'm going to pull that x up into the numerator by changing the sign of its exponent. And now I'm ready to find the derivative using the constant multiple rule. The derivative of 2 times something is 2 times the derivative of that something. Using the power rule, that's the old power, negative 1, times x to the reduced by 1 power, be careful, negative 2. And so that answer is, in simplified form, negative 2 divided by x squared. Please make sure you're familiar with the algebra that I'm using in these examples for simplifying and rewriting. Make sure you can do all of that correctly. All right, f of t is 4t squared divided by 5. This one I'm going to prefer to rewrite that as the constant 4/5 times the function t squared. So, oops, since it's function notation, I'm going to use prime for my derivative. So that'll be f prime of t, and that'll be the constant 4/5 multiplied by the derivative of that function of t. Take the old power 2 times t to the reduced by 1 power, so 2 minus 1 is 1, and simplifying you get 8t over 5. Or if you prefer, and sometimes I will say this is a preference that I would have, that's 8/5 times t. It's nice to see a coefficient separate from the powers of your variable. A lot of times it's for clarity's sake. Okay, y equals 2 square roots of x. Again, radicals in calculus are not necessarily our friends, and so I'm going to rewrite that immediately as 2 times x to the 1/2. So, oops, I don't need an equal sign. What am I saying? The derivative of that function with respect to x, so dy dx, is 2 times the old power 1/2 times x to the reduced by 1 power. 1/2 minus 1 is negative 1/2. Okay, so in my head I'm thinking 2 times 1/2 is 1, so the constant's kind of gone. Then I'm going to rewrite that without the negative exponent as 1 over x to the 1/2. And then I'm going to remember, oh yeah, when that fraction has 1 as a numerator, 1 over 2 is the power of x. I asked you to rewrite that in radical form. So that would be square root of x. You may, in pre-calculus, have done a lot of work with radicals in a denominator, and you probably found out that those are not that good. And so we rationalize them. And I still want you to do so when it's numbers. So like 1 over square root of 2, I'd want you to rewrite that as square root of 2 over 2. But if it's a variable under the radical, I'm okay if you don't rationalize it. The answer I'm leaving there is a good final answer. Okay, y equals 1 over 2 cube roots of x squared. So I want to rewrite that. The constant part is 1 over 2. Then the power of x that I'm going to have is, I'm going to have to introduce a negative to take it out of the denominator. And the power that we'll get when we have cube root of x squared is a power of 2/3. And of course it's negative because we're taking it out of the denominator. So that's x to the negative 2/3. So our derivative, dy dx, our derivative of y with respect to x, is going to be the constant times the old power times x to the reduced by 1 power. Negative 2/3 minus 1 is negative 5/3. And so simplifying that, I get negative 1/3 x to the negative 5/3. But I've said I don't want negative exponents, so that would be negative 1 over 3 x to the 5/3. And that would be an acceptable final answer for that one. Okay. F y equals negative 3x over 2. I'm going to rewrite that as negative 3/2 multiplied by x And so its derivative, I'm using the notation I haven't used much, y prime. It's the same thing as dy dx. I'm just using it just because I can. No other reason. Sorry, started to write something wrong. So the derivative of the function we have is going to be the constant (-3/2) times the derivative of the function. The derivative of x is 1, and so the derivative of our function simplifies to be (-3/2). All right. So now the next derivative rule I want to show you involves sum and difference. I think I'll prove this one for you, but I'm only going to do one of them, and as it turns out, if it's addition, which is the one I'm going to prove, or subtraction, you end up getting basically the same thing. So according to our derivative rule, for any function that we don't know how to get the derivative of, we're going to have to use f, which maybe I'll call it h, because I've already used f as something else. So, oops, I'm sorry, I forgot to write that. That will be the limit. Remember, we're going back to the definition of derivative. As delta x approaches 0, I'm going to use h because f is being used for something else. H of x plus delta x minus h of x all over delta x. So in other words, I'm redefining y to be h of x. And so another way we could have written that derivative would have been h prime of x. Okay, so by substitution into that sum of two things, we're going to put x plus delta x in for each x. So that will be f of x plus delta x minus g of x plus delta x. Okay, that's h of x plus delta x minus h of x, which is f of x plus g of x, all over delta x So what I'd like to do now is I'd like to get all of the f things together, separated sort of from the g things. So I'm going to say f of x plus delta x minus f of x. Okay, that's the f stuff. Then I'll have minus g of x plus delta x plus g of x. Be very careful there with your signs. Make sure you haven't made any mistakes with that. That's why I paused for a second to make sure I was doing everything correctly. Oh, I see what I did wrong. This is a plus. That's what I did wrong. Because I accidentally looked at that minus in the second line and I kind of lost sight of that plus. So that's supposed to be a plus. So that's where I messed up. So this should have been a plus, and this would have been a minus. See, I told you to be really careful, and then I messed it up. So there we go. Now it looks right. Whew. I was looking at it and thinking, oh my gosh, that is just so wrong. But I found my error, which is good. Okay, now you know an algebraic thing that I hope you've heard before, so I'll say it. now so that you get it. If you're adding fractions that have the same denominator, or subtracting, you add or subtract the numerators and put it over the common denominator. That's a reversible thing. That means that you can take a fraction that is a polynomial over a monomial and split that into a number of fractions, and that's what I want to do here. So I'm going to make this f of x plus delta x minus f of x over the common denominator delta x plus g of x plus delta x minus g of x all over delta x. Now I'm going to use that property of limits. It says if I have the limit of a sum, I can take the limit of the first thing plus the limit of the second thing, takes a long time to write. Sorry about that. Plus the limit of the second thing. And luckily I found my mistake and this is now correct. I'd like for you to look at that first limit expression and tell me where you've seen that before. Think about it a second. That first limit expression of the two, what is that? Well, that's the definition of the derivative of f. So that first thing is f prime of x. Plus, and the second thing is actually the definition of the derivative of g of x. So we could call that g prime of x. And so the derivative rule is this. If you have a sum of two functions, the derivative of the sum of two functions is the sum of their derivatives. So take the derivative of the first thing plus the derivative of the second thing. That's it. That's all you have to do. And by the way, we could do this proof if that had been minus. This would have been minus here, and this would have been minus here. So the derivative of a difference of two functions is the difference of their derivatives. Okay, so I'm going to do examples of this in the next part. So this ends part 1, and we will now go to part 2.